Good morning, all. Thank you for joining us for today's webinar. Before starting the webinar, I kindly request everyone to mute their microphones. And if you have any query or questions during the webinar, during the presentation, you can post it in the chat box. And after the webinar, there will be a discussion session where you can interact with the resource person and he will answer your queries and questions. Let us formally start this webinar. So to start the webinar, I invite Srimati Asha Ratish, Assistant Professor, Department of Chemistry, to formally welcome the gathering.
A warm good morning to all of you. Respected Principal Dr. P.P. Sharmila Ma'am, Chief Guest of the Day, Dr. Christie Thomas Cherian Sir, IQAC Coordinator Ms. Elvin Paul, Head of the Department Google Sir, Technical Committee members of the webinar series, colleagues, and all those who are gathered here, a warm welcome to all of you. With immense pleasure, I would like to introduce and welcome our chief guest, Dr. Christie Thomas Cherian Sir, an eminent personality having a very good profile, currently working as an assistant professor, Department of Physics, Christ University, deemed to be University Bangalore. He had his degree from Mahatma Gandhi University and Master of Science from Cochin University and postdoctoral degree from National University Bangalore. He had several publications in national and international journals and secured awards and honors from reputed universities for his academic excellence. I deem it an honor and privilege for us, sir, to have you with us. I am sure we will be enriched by the seminar. On behalf of the Department of Chemistry and MPMM Trust College and all those who gathered here, I welcome you, sir. Once again, I welcome you, sir. Thank you. Over to you, sir.
Okay, thank you. Shall we present? Yeah.
Participants kindly pin Dr. Christie Thomas in the people's list so that you can see his presentation.
Okay, am I audible?
Yes, sir, you are audible.
Okay, the PowerPoint can be seen, right?
Yes, sir.
Yeah, okay, great. Okay, thank you for the introduction, and once again, thank you for inviting me for this lecture. Today I selected the topic. This topic: mass transport in two-dimensional materials. Okay, so I have been informed that most of the participants might be students. So I would like to start from the scratch. Okay, so from the title, you might be wondering, at least a few of you might be wondering, what is two-dimensional material? What is a two-dimensional material? And what does it mean by mass transport in two-dimensional materials? Okay, I will give an introduction to two-dimensional materials. What is two-dimensional material? And then I will talk about the mass transport. Mass transport in the sense, it could be ionic transport, it could be water molecule flowing through two-dimensional material, or it could be gas molecules. Okay, so I will give a brief introduction on two-dimensional material and then shift to mass transport to two-dimensional materials. Okay, so the topic will be, there won't be much physics and there won't be much chemistry. It will be like a general talk. I won't be going deep into the subject. My intention is to give you a flavor of the research going on in two-dimensional materials. Okay, so as the as SMM said, I am working in Department of Physics and Electronics in Christ Dept University. We have some excellent research faculties as well as facilities like XRD, Raman, SEM, and conventional furnaces, FTIR, photoluminescence spectroscopes, etc. Okay, so let's start. I don't know how many of you have heard about graphene. Okay, I'm not sure how many of you have heard about graphene. Graphene is basically a single atom thick sheet of carbon atom. Okay, a single atom thick sheet of carbon atom. That's what you see artist representation of graphene. Okay, it's a single atom thick sheet of carbon. And what you see in that blue image or the bottom image is a microscopic image. Okay, if you look at graphene, how does it look under microscope? Okay, so what you see very bright, you can see a very bright substance, a white colored substance that is graphite actually. Okay, you know what is graphite? Graphite is like a form of carbon, like a bulk form of carbon. Okay, so that is basically graphite. And what I highlighted is the graphene, which is the single layer of carbon atom. Single layer of carbon atom has been highlighted, and that's how graphene looks under microscope. Okay, okay. So graphene is the thinnest 2D material. The bulk material we talk about, like it's 3D form. It's in 3D form. If you cut down one dimension of that 3D or bulk material, it will become a 2D material. Okay, so layered materials have been studied scientifically for more than 150 years. Okay, however, recently only we have begun to realize the true potential of these systems. Okay, I could say that's after the discovery of graphene. Okay, after the discovery of graphene, many 2D materials came into the picture. Okay, so each layered material, so basically the bulk layered material, when it is thinned down to its physical limits, exhibits some novel properties different from its bulk counterpart. Okay, so that's why 2D material is very important. When the bulk 3D form is thinned down to its physical limits, so the properties in bulk form changes. A few novel new properties starts to emerge. Okay, so apart from graphene, beyond graphene, now there is a wide spectrum of materials. For example, 2D boron nitride, which is an insulator, niobium selenide, and some kind of complex copper oxide. These are superconductors in 2D form. Okay, all these are 2D materials, or the bulk, when it is thinned down to its 2D form, it shows very unique properties. And also molybdenum sulfide, two-dimensional molybdenum sulfide is also possible. So a lot of such 2D materials are already there. Okay, I hope you got an introduction to 2D material. And as you all know, graphene is a semi-metal, or you can say zero band gap. But the researchers have shown that the band gap of graphene can be tuned. Okay. On the other hand, the boron nitride, 2D material, 2D boron nitride is insulator, having almost 6 electron volt band gap. And MOS2 also, MOS2 is a semiconductor. So in this 2D material family, we have semi-metal, metal, superconductor, insulator, semiconductors, everything is there in this family. Okay. So how to make 2D materials? You might be wondering, okay, fair enough, how to make a 2D material. Okay. So a lot of 2D materials have been already synthesized. Okay, the most common approach is a bit it's mainly by mechanical exfoliation. Okay, so mechanical exfoliation of single crystals. Okay, so you make single crystals, you grow single crystals. Chemistry people might be knowing how to grow single crystals, and then mechanical exfoliation. So you know that graphene has been awarded, the discovery of graphene and its unique properties have been awarded Nobel Prize in, I think, in 2009 or something. That Nobel laureates, what they did was they took a graphite piece like or HOPG and used a scotch tape. Okay, used a scotch tape to peel off, to mechanically peel off a single layer of carbon atom. That's called scotch tape technique. Okay, it's a very simple technique. So that basically that is a top-down approach. Top-down means from 3D bulk, you are thinning it down to 2D material. So you can use any kind of mechanical or chemical exfoliation techniques. Okay, that's what I have seen here, shown here. You can see a scotch tape, and this scotch tape can peel off a single layer of carbon atom from a graphite piece. Chemical exfoliation is also possible. Another possibility is bottom up. Bottom up in the sense you assemble the carbon atoms to form a graphene sheet. Okay, so that's what bottom up. You start from molecules. Okay, the conventional method is CVD growth, so, chemical vapor deposition of graphene. Usually it is done in some kind of metals, like copper is conventional substrate on which the graphene can be grown. Some precursor like methane will be used, and at high temperature it breaks down and form graphene, graphene coating on copper. Later this graphene can be taken out from copper. Okay, so these are the conventional methods to make 2D materials. Okay, so a little bit of physics. You know that about the band structure, energy dispersion relation in a conventional semiconductor material or a metallic material. The energy dispersion relation is given by is proportional to k square. Okay, so but here actually the energy momentum relation, energy wave vector relation is quadratic. Okay, but here in graphene, the main difference is the energy dispersion relation is linear. Okay, the pi band electronic, that's what you can see here, the pi band electronic dispersion. Let me take the laser pointer. Yeah. So the pi band electronic band structure. The band structure has been shown here, and you can see that the dispersion is found to be linear. The dispersion is found to be linear near the corners of the Brillouin zone. Okay, so dispersion is found to be linear compared to quadratic the relation in other materials. Okay, so electronic properties of graphene can thus be described by an effective massless Dirac fermion. Okay, Dirac fermion model. So basically the charge carriers are it acts as if it is massless. Okay, it acts as if it is massless particles, massless quasi-particles. Okay, so that is in terms of band structure, that is very important point for graphene, which is the linear energy dispersion relation. And one important thing is that the carrier density can be easily tuned. Carrier density can be easily tuned by changing the backgate voltage. Okay, so that is a little bit about electronic properties of graphene. Then let's talk about molybdenum sulfide. What's special about molybdenum sulfide? So as you all may know, the bulk MOS2 crystal is an indirect semiconductor with a, like in the range of 1.2 3 electron volt. Okay, bulk MOS2 is an indirect band gap semiconductor. You know what is meant by indirect and direct band gap semiconductor. For indirect band gap material, the band gap luminescence will be weak phonon assisted process. Okay, there will be a lot of loss, phonon loss. So the quantum yield will be very less. Okay, but an appreciable photoluminescence was observed in a few layer MOS2 samples, and most surprisingly, very bright photoluminescence was detected in monolayer MOS2. Okay, that's what you see here. The red curve is one layer MOS2, and the green curve is two layer MOS2. Okay, you can see a strong PL peak for one layer MOS2, and for two layer it's comparatively very weak. Okay, so and also in the inset, I think it's not clear. The y-axis is quantum yield. Okay, versus the layer number. Layer number means number of layers of MOS2. So you can see that as the layer number decreases, the PL quantum yield, photoluminescence quantum yield, increases as the number of layer decreases. Okay, so basically it has been seen that this indirect band gap MOS2 in bulk form is getting converted to direct band gap material when it is thinned down to 2D material. Okay, which is quite interesting. Okay, let's go to another possibility with 2D material. You all know what is van der Waals force. It's a weak force acting between surfaces and molecules. These atomically thin surfaces can interact each other via van der Waals interaction. Okay, van der Waals force. So these 2D materials we talked about, okay, can be assembled into van der Waals heterostructures. Van der Waals heterostructures are made up of different two-dimensional materials, two-dimensional layers stacked upon each other to form a single stack, giving really different property compared to its constituent blocks. Okay, you can assume it as Lego blocks. Some of at least a few of might have seen or played using Lego blocks. Okay, so each of these colors can be a 2D material. Okay, and these 2D materials can be stacked. Why? There will be a interaction, van der Waals interaction between these 2D materials. Okay, so actually there will be an in-plane strong covalent bond. This strong covalent bond provide in-plane stability for 2D material. Okay, and out of the plane, that means between the 2D materials, there it will be van der Waals heterostructures. Okay. And why it is called van der Waals heterostructures? Because these atomically thin layers are not mixed through a chemical reaction or anything. Okay, but rather these thin atomic layers are attached by a weak van der Waals interaction. That's why it's called van der Waals heterostructures. Okay, I will show you just an example. All these are 2D material family, a few selected members of 2D material family, graphene, boron nitrate, like that. Okay, and some, if you dope with fluorine and some other kind of stuffs, you can get graphene. So you can consider these as Lego blocks, and you can make structures out of it. Okay, and these structures give like really different properties compared to its constituent material. Okay, so this is called van der Waals heterostructures. So these are the different possibilities. So this is a graphene boron nitrate stack. A lot of research is happening in this field. And already a group showed light emitting diodes, like nanoscale light emitting diodes devices using this kind of van der Waals heterostructures. because you can tune the band structure of the whole stack. Okay, one more interesting property is the van der Waals pressure. Okay, van der Waals pressure. What is that? Okay, so I talked about heterostructures, and in this van der Waals heterostructures, there is a possibility that few molecules can get trapped between the two-dimensional crystals. There is a possibility that when you make the heterostructures, molecules can get trapped inside this between the two-dimensional crystals. Like maybe you can consider a salt molecule, a salt or a water molecule. The problem is that these molecules, when it gets trapped between these two atomically thin structures, what happens is that it feels as if it is inside a pressure cooker. Okay, that means it feels a lot of pressure. Okay, the trapped molecules are predicted to experience pressure of as high as 1 gigapascal. Okay, estimated pressure is 1 gigapascal. Okay, so what is the significance of this? Because this pressure can induce chemical reactions which can happen only at high temperatures. This high pressure can induce chemical reactions which may happen only at high temperatures. Okay, so we have seen that our research has shown that several trapped salts are found to react with water at room temperature, and leading to two-dimensional crystals of corresponding oxides. Okay, these salts are getting converted to corresponding two-dimensional oxides. Okay, so this acts as a pressure cooker, I would say. So a lot of chemical reactions, unique chemical reactions can happen inside this heterostructures if a molecule is getting trapped. Okay. So now I have given you an overview about 2D materials and what all researchers have are happening in this field. Okay. Now I will go to the second part of my talk, which is basically molecular transport through these 2D materials. Okay, molecular transport through these 2D materials. Okay, I hope you have heard about carbon nanotubes. Okay, and if you search in Google fast water transport through carbon nanotubes, you will get a lot of research papers. Okay, for I think it's almost last 10 to 15 years, a lot of research is happening in measuring the water transport through carbon nanotubes. Why it is very important, very interesting? Why it is interesting? Because it has been measured that water goes through carbon nanotubes very fast, exceptional flow rate or exceptional speed with which water moves through them. So water moves through the carbon nanotubes with exceptional speed. So okay, fair enough. What is the importance of that? Because then carbon nanotubes can be used for desalination applications. Okay, because if water goes through it very fast, for desalination, what we want is water on the other side. If it can block some salts also, it would be wonderful. Okay, so people were trying to understand why this is happening. Okay, why water is flowing very fast inside carbon nanotubes. Okay, so one reason is kind of molecular ordering phenomena. Molecular ordering, you can imagine it as a train. Okay, train going through the rail track. Okay, basically the water goes as a single file inside the carbon nanotubes. Okay, the main reason is that it won't interact with the surface of the carbon nanotube. Okay, and it goes as a single file, okay, or single train of water molecules inside the carbon nanotube. Okay, so basically water molecules are going in an ordered manner inside carbon nanotubes. So a group from France, they have studied or compared the flow through carbon nanotubes, as well as boron nitrate nanotubes. Why they compared carbon nanotubes and boron nitrate nanotubes? Because they are crystallographically similar. They are crystallographically similar, but electronically different. Carbon nanotube is like semiconducting or metallic in nature. Boron nitrate nanotubes has insulating nature. Okay, so they studied two materials which are crystallographically similar. So here you can see the radius of the nanotubes in x-axis, and y-axis you can see slip length. What is slip length? Have you heard about slip length before? Okay, so I can explain. Slip length, basically it's a measure of I can say the friction between the solid and liquid. Okay, let's say water going through a pipe. Okay, so the water layer in contact with the pipe, the outermost water layer which is in contact with the pipe interacts with the pipe. Okay, so that gives rise to some kind of friction. Interaction gives rise to some kind of friction in flow. Okay, so slip length is the measure of friction. Okay, larger slip length indicates the liquid flow between the surface experience a low friction. Okay, larger slip length denotes lower friction. Okay, you might be studied in BSc first year or something when you consider kinetic theory of gases and all. You consider that the layer which is immediately on top of the layer of molecules immediately on top of the surface is at rest, or layer of gas molecules immediately on top of the surface is at rest. Okay, so that rest, that velocity zero is due to the interaction or friction between that surface and the layer of water or gas molecule. So larger the slip length indicates lower the friction. So they studied a radius dependent slip length measurement, and they saw that for carbon nanotubes, slip length increases when you reduce the radius. Okay, that's what you see. When you reduce the radius, slip length increases. That means water has carbon nanotubes offers very low friction to water molecules when the diameter, you can see here the slip length going up. Okay, as the CNT diameter reduces, the slip length increases, whereas boron nitrate nanotube, you can see the slip length remains the same. Okay, so because of these nanofluidics means the transport of fluids in nanomaterials. Okay, so that is the study of nanofluidics is very important. Or why? Because a lot of interesting phenomena emerge in nanoscale. Okay, so study of fluid transport in 2D capillaries are very important. Okay, so coming to next slide. Yeah. So here you can see a graphene membrane. Okay, graphene, I already told graphene is a one atom thick membrane, one atom thick carbon layer. Okay, interesting property of graphene is its impermeability. It is impermeable. A single layer of graphene is impermeable to everything. I would say everything, impermeable to water, gas, and all. I meant a perfect graphene without any defects. It's impermeable to everything. So whether it's a gas or water, it is impermeable. Why? So graphenes graphene's sp2 orbitals forms a dense delocalized cloud of electrons. Okay, it has sp2 orbitals. It forms delocalized electron clouds, and that blocks the gap within its aromatic ring. Okay, you can think about that aromatic ring of like that graphene, and the gap in that aromatic ring is blocked by the dense delocalized electron cloud. Okay, but you can put artificial pores inside graphene, artificial pores on graphene. That's what you see here. You can put artificial pores on graphene. Look at the laser pointer. You can see, using high energy radiation, you can put artificial pores on the graphene and make graphene to selectively allow certain molecules to go through. For example, you can control the size of the pores in such a way that it allows just water molecules to pass through and block ions. You can, I repeat, you can control the size of these artificial pores in such a way that it allows water molecules to go through, but the larger ion molecules will be blocked. Then it can be used as a desalination membrane. It blocks ions and water molecules go through. Okay, but the problem with this is that this cannot be industrially scaled up. Okay, the single layer graphene production of single layer graphene and its and putting holes on this single layer graphene is not really a viable approach. Okay, so we have to look for some other alternatives. Okay, and there comes graphene oxide. Okay, what is graphene oxide? I know at least a few of you might be working on graphene oxide because it's easy to synthesis and in our lab scenario. Okay, graphene oxide is nothing but oxygen functional groups attached to a graphene sheet. That's all. Graphene oxide is nothing but oxygen functional groups attached to graphene sheet. You can say there will be 40 to 60% of function, 40 to 60% of graphene oxide sheet will be functionalized. Okay, so you can imagine it as pure graphene parts as well as functionalized one. For a graphene oxide sheet, there will be pure graphene part as well as oxygen functionalized portions as well. Okay, what is the beauty of graphene oxide is that it can be produced in a large scale. Okay, what I have shown here is just a few milliliters, but it can be industrially scalable. A company called Graphenia, they makes and sell graphene oxide water dispersion. Okay, actually, this graphene oxide can be stacked. Okay, this you can see the SCM image. It can be stacked together. Why it stacks? Because there are oxygen functional groups, and these oxygen functional groups interact with each other. These are millions of sheets of graphene. What you see here in the SCM image is the millions of graphene sheets, stacked on top of each other. And you can imagine like a nano channel between each stacked graphene oxide sheets. Okay, so this is a stacked graphene oxide sheet or membrane. Okay, so what you see in the SCM is a cross-sectional image of a graphene oxide membrane with graphene sheets stacked on top of each other. Okay, so what are the advantages of this graphene membrane? Okay, so I have to say that it can be mass produced. It can be coated. This is a graphene oxide coated on a sheet in an A4 size scale on a PET substrate. Okay. Okay, so how can we make graphene oxide membrane? It is very easy. If you have GO solution, graphene oxide solution, just drop cast it, evaporate it, you will get a stack, ordered stack of graphene membrane, graphene oxide membrane, or you can vacuum filter it, you will get a graphene membrane. You can spray coat it, you can use Dr. Blade technique. There are different methods. Okay, so basically, the most important point is the stacking of graphene sheets. That's what you see here. The graphene oxide sheets, the atomically thin graphene oxide sheets stacked to form a proper membrane. And now you have to ask that question, how molecules pass through this material. Okay, so the one possibility is it can go like a tortuous path. Okay, it can form a tortuous path as shown here. Okay, through the graphene interlayer space. You can see an interlayer space between the graphene sheets, and actually that is nanocapillary. You can say it as you can call it as nanocapillary. So this interlayer space is utilized for the movement of water molecules or any other molecules. Okay, so you can say that molecular permeation is controlled by this. It's believed to occur along this graphene channels, and molecular permeation is controlled by the stacking or controlled by the despacing. Despacing means the distance interlayer spacing. Here despacing means interlayer spacing or the spacing between two graphene sheets. Okay, where the image you see here is a few micrometer thick graphene oxide membrane. Okay. Okay, what is the speciality of this graphene oxide membrane? You can see here, water goes through. So if you take a micrometer thick geomembrane, water goes very fast. Through a micrometer thick geomembrane, water goes very fast, orders of magnitude larger than organic solvents or other gas molecules. Okay, so if you take a 2 micrometer thick graphene oxide membrane, all gases as well as organic solvents will be blocked, but good thing is that water goes through. Okay, so it has it is highly permeable to water. Water permeate at least like orders of magnitude faster than helium or other gases. Okay. Okay, why is it so? Why water permeates very fast? So actually the permeability or water permeation, if you use the standard Newtonian flow, if you assume standard Newtonian flow and use Huygens-Poiseuille equation, you won't get the exact, if you theoretically calculate the permeation, you won't get value similar to experimentally observed value. Experimentally observed value will be orders of magnitude larger than that of theoretical value. Okay, so but when you introduce slip length as well as a capillary pressure of 1000 bar, you will get experimental as well as theoretical value almost close. Okay, so it has been assumed that there is a huge capillary pressure inside the graphene capillary, inside this nanocapillaries, as well as the slip length. Okay, I already talked about slip length. That contributes to the fast permeation of water. So you can imagine it as so you can see two graphene oxide sheets with oxygen functional groups. So these oxygen functional groups acts as spaces. This oxygen functional group acts as spaces. That means it controls the despacing. It controls the despacing or the interlayer spacing between two graphene sheets. So proof for that is coming from this graph This is basically the interlayer spacing versus RH. That means the graphene membrane has been kept in different RH, including liquid water. You can see liquid water as well, including liquid water. RH means relative humidity. Okay, so as the humidity increases, the interlayer spacing increases. That you can clearly see here. As the humidity increases, interlayer spacing increases. Okay, and in the liquid water, the interlayer spacing goes up to 14 angstrom. Okay, so the flow is controlled by the interlayer distance, or the molecular permeation is playing a crucial role in the flow rate. And also you can see that the interlayer space is RH dependent. The D spacing is RH dependent. Depends on relative humidity. Depends on relative humidity means it depends on how much water the graphene oxide can intake. Or if I put it in another way, when I put graphene oxide inside liquid water, it swells and interlayer spacing increases to 14 angstrom. That's what you see here in this graph. This is basically a simple XRD experiment. Okay. Okay, so this is a typical experiment we do. We make graphene oxide membrane. You can also do this. Make a YouTube setup. Okay, and graphene oxide membrane will be kept in between. That's what you see here. And one side there will be feed, and other side will be permeate. Feed will be having iron like salt solution. Okay, what we observed was, you can see here that so the x-axis is the hydrated radius of the different ions or salt solutions we used, and y-axis shows the permeation rate. So you can see that the permeation rate drastically goes down when the hydrated radius of the ion goes beyond 4.5 angstrom. Okay, when the hydrated radius goes beyond 4.5 angstrom, the permeation drastically goes down and it goes below the detection limit. Okay, so what does it mean? It means that graphene oxide can act as a molecular sieve. It can act as a molecular sieve with a cutoff at a hydrated radius of 4.5 angstrom. Molecular sieve means like a sieve you use for filtering your tea. Okay, so here that graphene oxide can act as a sieve with a cutoff at 4.5 angstrom in wet condition. Okay, all the molecules having hydrated radius greater than 4.5 angstrom will be cut off. Okay, but there is a problem. As you can see here, most of the salts we are interested in is going through graphene oxide membrane. Okay, so their use in ion sieving or desalination technology is limited by this permeation cutoff at 4. This is radial, so permeation cutoff diameter of 9 angstrom. Okay, so how can we solve that issue? We need to cut off the salts as well. Then only we can use for desalination purposes. So as I discussed before, when you put graphene oxide in water, it swells, right? So we need to restrict that swelling. We need to restrict that swelling. How can we restrict that swelling? As I shown you in this graph, you can see in this graph, if the interlayer spacing is in this range, like less than 10 angstrom, if the interlayer spacing is less than 10 angstrom, you can possibly cut off salts. But I won't get interlayer spacing in this range, because when I put the graphene oxide in water, because we always do in water, right? Experiment with water, it swells. So if I can restrict the swelling, it would be great. So what we tried is we physically confined GEO. What you see here is a graphene oxide membrane in the black portion. That the SCM picture of that black portion is here. You can see as it's like stacked graphene sheets. You can see, and the yellow portion is an epoxy, like a glue, okay, a powerful glue, okay, and that can physically confine GEO from expanding or swelling when it is put inside water. Okay, so basically we made a tunable interlayer capillary, okay, using by physical confinement approach. Tunable interlayer capillaries inside graphene oxide by physically confining this GEO using epoxy. There are a lot of studies already undergoing by chemically restricting. We use physical restriction. You can use different functional groups to chemically restrict the swelling. So the most important point here is that, so once we restrict the swelling, use physical confinement, what we observe, so here you see the left hand side, you see different capillary sizes: 9.8, 9 angstrom, 8.6, 7.4, 6.4 angstrom. So we made graphene oxide membrane having different capillary sizes. Okay, how we made it? By controlling the RH. Okay, by controlling the RH, we can tune the D-spacing, and then by physically confining, we can keep that capillary size. So 9.8, 9, 8.6, different capillaries, different graphene oxide membranes of different sizes, capillary sizes have been made, and you can see that as the capillary sizes goes down, the salt gets rejected. Okay, as the capillary size goes down, the salts get rejected. For the highest capillary, 9.8 angstrom, you can see that Mg2 plus is getting rejected. But if you look at that purple one, the purple color, 6.4 angstrom capillary or geomembrane, you can see all the salts are getting rejected. But now you might be wondering, it is a complete closure, nothing is going through. So you have used glue and all, nothing is going through. That's the reason. No, water is still going through. Okay, at the same time, the ions are getting rejected. Okay, you can see in the right side, the permeation rate, so the black, you can look at, there are two y-axis. One is the ion permeation rate, and the other one, the blue one, is water permeation rate. If you look closely, the ion permeation rate, one y-axis is in exponential scale, and other one is linear scale. So as the interlayer spacing decreases, the ion permeation decreases exponentially. Ion permeation decreases exponentially, but water permeation is decreasing only a few times. Whereas the interlayer spacing decreases, ion permeation decreases exponentially, whereas water permeation is only decreasing just a few times. That means if you go from 9.8 angstrom to 9.8 angstrom to, let's say, 7.9 angstrom, you can see that water permeation is only changing 2 times, decreasing 2 times, whereas ion permeation decreased almost few orders of magnitude, which is really good for desalination. You can block ions, at the same time you can get water flow through. Okay, why is it so? Actually, you know that in bulk solution, water molecules stabilize ions by forming, and chemistry students know this very well, water molecules stabilize ions by forming concentric hydration shell, okay, in a bulk solution. So now for an ion to enter the channel with a capillary size less than its diameter, so an ion is approaching a capillary size having size less than its diameter, what some water molecules some water molecules must be removed from the hydration shell, or it will get squeezed. You can see a simulation. You can see here that the water molecules will get squeezed to go through. But higher the ion charge, for example, Mg2 plus, Mg2 plus and Na plus, okay? Higher the charge, higher the ion charge, stronger it attracts water molecules. Okay, so accordingly, ions with larger hydration energy, for ions having larger hydration energy, tougher water shells are expected. So tougher the water shell, larger barrier for entry into these nanocapillaries. So if tougher the hydration shell or higher the hydration free energy, it will be more difficult for such an ion to enter this capillary. Okay, basically because this water molecule gets squeezed to for the ionic entry into the capillary. So ion selectivity is defined by the hydration free energy of ion dehydration free energy. Okay, so so I will quickly go through like a smart geomembrane. Basically smart membrane in the sense you can modify its permeation or its properties by applying an external stimuli. Okay, that's simple as smart geomembrane or smart membranes. Using some external stimuli like temperature or electric field or a magnetic field or something like that, you can tune the geomembrane. So here I will quickly go through this. We can electrically control the water permeation. By applying an electric field, you can control the water permeation through graphene oxide membrane. So here it is a schematic representation of our setup where you can see graphene oxide membrane, and it has been coated on both sides with electrodes. One side is gold and other side is silver. Okay, so that we can apply electric field across it. You know that graphene oxide is insulated. Okay, and these electrodes are porous. Why? Because I want to measure the water permeation when I apply electric field. Okay, so I will skip this. Maybe this is better. So what we observed was, I will play this video. Yeah, you can see here water is going through when the current is 0, but when current is increased, you can see water permeation stopped. Okay, and when current is released, I mean current is reduced to 0, again water permeation. Okay, I will play it again. So you can see water flow going through at 0 per milliampere, but when it increased to 200 milliamps, the water permeation stopped. Okay, so that's what we observe. So I'm not going into details of this. In this image, in this schematic image, you can see a blue channel like thing. Okay, so basically these are conductive filaments in graphene oxide membranes. So we intentionally made conducting filaments in graphene oxide membrane via controllable electric breakdown. So basically, if you apply electric field across an insulator after a threshold voltage, there will be electrically conducting channels formed inside an insulator. Okay, basically that's what we did. We created conductive filaments in graphene oxide membranes, and you can recollect your +2 electrostatics knowledge. Electric field that concentrate around these current carrying filaments ionize water molecules inside graphene capillaries. Okay, so there will be huge electric field produced around this current carrying filaments, and this huge electric field ionizes water molecules inside the graphene capillaries, and this ionized H3O plus or OH minus, these ionized molecules will be having very low mobility. So that because of that very low mobility, because it interacts with the graphene sheets, as well as it has large hydration shell so that it become immobile. Okay, there are various reasons because of this, because of the production of these ions, because of the ionization of water molecules, the water permeation stops. Okay, which is a very good observation. In the sense that we can tune the skipping this, tune the water permeation through graphene oxide membrane. So I'm winding up, and by just telling you what's the prospect of geomembranes. So now in this industrial scale desalination plants, we use polymer thin film composite membranes, polymer TFC membranes having 99.7 to 99.8 percentage of sodium chloride rejection. Okay, and 50% recovery, and the flow rate is 1 liter per meter square per hour per bar. 50% recovery. What do you mean? What is that 50% recovery? If any one of you are using a filtration unit in your house, you can see that lot of water will be wasted as like byproduct. You will be getting pure water as well as a wastewater. Okay, so 50% recovery in the sense 50% of input water can be recovered. Okay, that's what 50% recovery. Okay, and this membrane work on solution diffusion mechanism. Okay, in graphene oxide membrane, it works on like I told you, the selectivity is defined by ion dehydration, and basically this is a geometric rejection. In geomembranes, it's basically size exclusion mechanism. In polymer TFC membranes, it's solution diffusion mechanism. It has poor rejection to some molecules, organic molecule. It is very good in rejecting water molecules, but it has very poor rejection to organic molecules. Okay, why that is important? Because in an industrial plant, 50% of total energy, 50% of total energy invested for post and pre-treatment of water. Post and pre-treatment of water. Why? Because this membrane has poor rejection to some molecules which are harmful for human beings. Okay, so this 50% of energy is wasted for pre-treatment and post-treatment. Okay, there comes the importance of geomembranes. Okay, here you can see a selectivity permeability trade-off. So you can see that as water permeability in typical membranes, as water permeability increases, the selectivity goes down, which is a kind of trade-off. In a typical polymer membrane, when water permeability increases, selectivity goes down. But in geomembrane, you can get selectivity as well as high water permeability at the same time. You can see a tick mark here. Okay, so geo comes here. Like it has higher selectivity as well as high water permeability. Actually, high water permeability has minimal impact because already the polymer TFC membranes have good water permeability, but the selectivity is very less. There comes the importance of geo. Geo has high water ion selectivity. It has finest sieve, and so that it can reduce the post-treatment and pre-treatment steps in a industrial plant. Okay, and also it can reduce the membrane fouling, but that is under investigation only. So that's the prospect of graphene oxide membrane. It can be used as you can reduce the graphene oxide. If the graphene oxide is reduced, you will get RGO, reduced graphene oxide membrane. It blocks all gases, liquids, and salts. It can be coated on steel or anything. It has really good chemical protection property. Like it doesn't react with chemicals. And also it can be used as paints. I will show you a video. One part of this brick is coated with graphene. This is not graphene oxide, this is reduced graphene. That means graphene paint. You can see that the coated part, water stays there, whereas in the uncoated part, water goes into the brick. So there are a lot of applications for this kind of graphene oxide or 2D material based applications. So I talked about exotic properties of 2D materials and fast water transport through graphene capillaries, and I told you that ion sieving can be achieved in graphene oxide membranes. And I also showed you potential applications in filtration and barrier coatings. Thank you.
Thank you, sir. Thank you for an informative session. The platform is now open for the students to interact with Dr. Christie Thomas. If you have any query, you can directly ask him. You can unmute yourself and ask.
I think the students have understood this. I think maybe that's why they don't have any query.
Students, interaction is the essence of webinar or seminar for that matter. Kindly interact, kindly ask your queries if you have any. You can unmute yourself and ask the query. It's a golden opportunity. Any queries? I think everyone is familiar with the subject.
I think I presented really clearly. That's why they don't have any doubts.
Sir, one question there. One question.
Yeah. This is only possible for water. Depending on the thickness, you can tune that. Okay. If you make graphene membrane very thin enough so that there will be a few pinholes come into the picture, pinholes in the membrane, and that will lead to the transport of alcohols as well. So basically, you can play with the thickness as well as the stacking. How good is the stacking? Okay, the thickness and the stacking leads to this material transport properties. Okay, what I said was at micrometer thick graphene oxide, if I take a micrometer thick graphene oxide, water goes very fast and all other stuffs will be blocked. Okay, but if you take a nanometer thick, like a 10 nanometer thick graphene oxide membrane on a substrate, then it will allow our organic molecules to go through. Okay, so basically thickness as well as the stacking, the efficiency of stacking determines the material transport.
Thank you, sir. Thank you, Sudhir. Any other query? Okay, shall we wind up, sir, then? Shall we wind up the session then? I think the questions are not coming.
Yeah.
Okay. Thank you, sir. I invite Mr. Gogul GK, Assistant Professor, Department of Chemistry, to formally deliver his word of thanks.
Good morning. We had a wonderful session on mass transport in two-dimensional materials by Dr. Christie Thomas Cherian. Assistant Professor, Department of Physics, Christ University, Bangalore. On behalf of Department of Chemistry and PMR Center College, I express my sincere gratitude to Dr. Cherian Thomas sir for this highly informative session. Thank you, sir.
Thank you. Thanks a lot.
I, on behalf of Department of Chemistry, would like to thank our principal, Dr. Sambala ma'am, IQSC coordinator, Elvin ma'am, and the coordinator of today's webinar, Ms. Asha PS, and the coordinator and technical committee of this webinar series, Dr. Nitin Venugopal and Dr. Ranjit PK, for their wholehearted support. Thank you. And I also would like to thank the teachers, research scholars, and the students for their active participation. Thank you all.
Thank you, sir. All participants are kindly requested to fill the feedback form. The link is given in the chat box, and the link is now open. You can register your attendance through that and receive e-certificates for the same. Thank you. Thank you for attending the webinar.